As discussed in the previous session, these parameters are variables of frequency. The parameters are Xc, XL, Z and I are the variables of frequency. There is one more parameter of LCR is power dissipation, is also a variable of frequency. Let us get the expression for power dissipation. The expression for power dissipation of this LCR, that is the usual notation for power dissipation. And in LCR, V, it is the voltage in LCR, it is the current in LCR. Current is this theta is equal to omega t. And there is a pi because there is a phase difference between the current and voltage in the LCR. The phase difference is pi. This is the equation. You have to solve this. Upon solving this equation, we get this equation. Solution of steps not shown. Directly I have written the equation. So power dissipation equals V into I. Here the mean values are RMS values and cos phi. Phi I said the phase difference between the current and voltage. In this equation, cos phi is power factor. It will decide when the power is minimum and the power is maximum. The power is maximum when the phase difference between the current and voltage is 0, that is cos 0 equals 1. Power dissipation is minimum when the phase difference between them is pi by 2, that is cos pi by 2. So let us talk about the maximum power dissipation at pi equals 0. Pi equals 0, that is phase difference is 0 between current and voltage. It is at resonant state, at the resonant condition. At the resonance condition, Xc is equal to SL. In this graph, we have XL and XC are in the opposite direction. When they are equal, they are getting cancelled. We left with only R. There is no phase difference between current and voltage in case of R. That is why condition for LCR for phase difference equals 0 is, that is phase difference is 0. This is a power dissipation which is maximum. The equation for that is this one. V into I, it is RMS value, RMS value. It is V, I. We can write the power dissipation only in terms of current. Substitute for V. The current into resistance. Resistance is impedance. I square Z is the power dissipation. The expression for power dissipation is I square Z. Look at this. Power is a function of current, I square. I said already, I is a function of frequency. then P must also a function of frequency. Here direct relationship. Then we get the graph similar to this. The graph similar to this power dissipation. Power dissipation in LCR is varying with frequency. This also verified by experimented on the LCR circuit. We have measured the values of power dissipation at different frequency values, and the graph is drawn between them. We get a curve like this, similar to the current curve. Here the maximum point, the point is similar to the point the state of resonance. The condition is resonance condition for LCR maximum. Here the point is called as point of maximum power dissipation. The power variation is it increases, reaches maximum and decreases like this. Point of maximum power dissipation. At the resonance state, already said, maximum possible current flows. Then at the state only, resonance state only, maximum power will be dissipated. If the maximum power is dissipated in the circuit, what does it mean? What is power dissipation? Power dissipation is actually the power used up in the circuit. Whatever the power used up will go as a useful form of work. Any useful form of work is done, then it is easier for this circuit. What is easier for the circuit? Easier for the flow of current. That is what we are seeing in the alternate way. Whether it is power dissipated or maximum current flow, both are same. Power is dissipated at maximum state, that is, of course, power is dissipated at the resistor. These two are not power dissipator, they are not power dissipator. Only they store up and release energy, these two. Electric power is dissipated through only resistor. So, with all these mathematical concepts and graphical representation, it is clearly understood there is one resonance condition where the frequency, that is, that frequency of AC, that frequency of AC is resonance frequency, easily pass through circuit, no restriction, and all other frequencies are getting filtered out, are getting blocked in this circuit. That is a concept you have understood by this. All this mathematical concept and graphical representation and the same experimental support shows that F naught is allowed freely. And the next question is, if there is LCR circuit, this LCR circuit has only one F naught value. No. A LCR circuit can have different possible values of F naught. LCR circuit can have different possible values of F naught because F naught value depending on the value of L, value of C. Depending on the value of L, value of C. What is value of L? Inductance value, capacitance value. That we understood by another mathematical approach. This is what the mathematical approach. At the resonance state, that is resonant frequency, this is what the equation satisfied. Substitute for them in terms of angular frequency, not because of resonance condition. And rewriting this equation, that is omega naught, omega square is equal to this one, and omega naught equals 1 by root of this right hand side. Substitute for angular frequency as linear frequency. Omega naught is equal to F naught equals this one. F naught equals 1 by 2 pi root of LC. Concentrate on this equation. Look at this F naught value. F naught value is not a constant value of LCR. It is depending on the value of L as well as value of C. Of course, it is inversely proportional to L and C. As L and C increases, F naught decreases and vice versa. But the value definitely depends on the value of L and C. The equation tells us that by changing the value of L or by changing the value of C, any one, both is also possible, but you choose any one of them. By changing the value of L or by changing the value of C, we can change the value of F naught. We can choose also F naught, whichever value we want to pass through, accordingly fixing L or C. This equation understood. Let us extend this theoretical concept to this LCR circuit. This LCR circuit, once it is constructed, it is possible to have inductor of variable inductance. Inductor of variable inductance. Devices are available. Capacitor of variable capacitance. Capacitor of variable capacitance. We can fix a knob or switch. Switch may be a digital switch, which is most commonly using today. By changing that knob or switch, we can able to change the value of L or value of C. By changing the value, that is by rotating the knob in the old radio system, in the old TV system, or by changing the switch, digital switch, of course in the remote, we can change the value of L or C. If value of L or C changes, value of F naught also changes. That means we can change from one F naught value to other F naught value. Only that F naught value is passed through, other are filtered out. That is a selection. Using the knob, we can select whatever frequency to pass through, whatever frequency you are able to access whatever broadcast station you are able to access for the information. That is the one decided by the knob of the switch. This is why we are using LCR for selection of frequency or selection of broadcast station, both in radio and as well as TV station, TV set. So that is the application as well. One way it is acting as a filter, and the other means we are using as a selector, selecting the different stations. And one more concept we need to understand here. Look at this signal. This signal is current signal. This signal is power dissipation signal. Both of them are same almost. In these signals are nothing but information signals. These signals are also known as information signals. The same current signal or power signals are also information signals, carrying information. Look at this signal. This signal is sharper. This signal is blunt. Sharp and blunt. This signal is narrow. Width is narrow. Difference between this frequency and this frequency, narrow. Band width, I say. And this width is larger. Difference between this frequency, band width is large. What difference we talk about these signals? And this signal and this signal, why they differ? Same frequency. We see the difference in the signal. The difference in the signal because of difference in resistance. What resistance? Resistance of the resistor. This is same as impedance. Resistance of resistor. If the resistance is less restriction for the flow of current, more current flow, less resistance, signal strength, current flow for the strength is more. The strength, what is that? Sharper the signal. So if the resistance is lower, the signal becomes more and more blunt. That is what. The difference we can, recognize. If you get this signal, if there is a radio, we get a sound or voice in the form of audio signal. We get a sharp signal, that is a clarity in voice. Only this frequency, this information is, we get maximum information. Clarity in voice. If you have a signal like this signal will allow this frequency as well as other frequencies in small amounts. These frequencies of other broadcast in small amounts, and interference takes place between these frequencies, giving distorted voice or sound. The audible sound is thus blurred, distorted voice you hear. Either in maybe audible signal or video signal. Video signal we see in the TV. TV. If the picture, if you have this kind of signal, the quality of picture in the video signal is very good clarity, very good picture. Quality of picture becomes very good clarity, high clarity. Here the clarity is not. If you have this signal like this LCR signal, you don't get a clarity. Blurred picture is blurred vision. Picture we see that because of interference of it allows so many other signals to pass through. So what is the condition? Whether you speak either in terms of the current signal or in the power signal, the same thing concept here. So for a sharper signal, the signal of what is that? The band, quality of band, narrow band for a lower resistance value. So always you look for this kind of signal, even more sharper signal. To get that, we always use LCR circuit of lowest possible resistance. LCR circuit of lowest possible resistance. If you have got LCR, then we get what is that? Any radio or transistor or any TV, we get what is that? Very good quality of sound, very good quality of picture as well as. So that is what this concept or the mathematical concept or theoretical concept we explain. What is the reason for using LCR and which LCR gives a good quality of audio signal as well as video signal. So with this we have completed this LCR and AC current. Thank you very much.